The Mathematical Methods Summer Examination paper from 2015. You have to answer all questions in section A and any three from section B. And the marks for the best 5 questions will be recorded. So for question number 2, which are my questions, part A, we want to determine whether these 3 vectors are linearly dependent or independent. For this mapping T from polynomials of degree 3 into 2 by 2 matrices, we want to determine whether or not T is a linear transformation. And for part C, we want to find the eigenvalues and eigenvectors of this 2 by 2 matrix. And finally, for part D, we want to prove that this mapping, phi, is not an inner product over 2 by 2 matrices. So if we look at question 2, part A, in order to prove that these 3 vectors are either linearly dependent or independent, it's easiest just to take the determinant of this matrix. So we write each vector as a row in the matrix, and that gives us a 3 by 3 determinant. We're going to expand around the first row, and if you evaluate each of these determinants, then we see that we get a total of 95 over 6. So that means because the determinant is non-zero, then these vectors are linearly independent. Of course, if the determinant was equal to 0, these vectors would be linearly dependent. So now we go on to part B. So we have this mapping from polynomials of degree 3 into 2 by 2 matrices. Now, because we're dividing here, you can't really divide or multiply terms for linear transformations. That gives us a clue that this is not going to be a linear transformation. And when it is not a linear transformation, we just need one counterexample. So in this particular case, we're going to take a vector u is x squared plus x cubed, which is in P3R. And we're going to take alpha is a real number, and we'll take that equal to 2 for this particular counterexample. For this example, we're going to show that t of alpha u is not the same as alpha t of u. So t of alpha u is t of 2 times this polynomial, which gives us t of the polynomial 2x squared plus 2x cubed. Now if we take the mapping of 2x squared plus 2x cubed, then we see the term in row 1, column 1 is a over b. A is 0. B, in this case, is also 0, so that doesn't really give us anything. And the non-zero term here is c over d. Okay, so c over d is 1. But alpha times t of u, that's 2 times t of x squared plus x cubed, and you can see that gives us 0, 0, 0, 2. So this is not a linear transformation. And you would have observed anyway, we have real problems here, because if b or d are 0, then we have infinities or numbers that are not defined. So this is definitely not a linear transformation. Now we go on to part C. So we want to find the eigenvalues and eigenvectors of this 2 by 2 matrix. So we subtract lambda on the diagonal, and then we find the determinant of A minus lambda I. So that gives us this 2 by 2 matrix. The determinant, so we do this term times this term, take away this term, that term, that times this term, and we get a quadratic equation in lambda. So this is called our characteristic equation. We can solve this characteristic equation, we can solve this quadratic, and you'll see it has roots at -3 and 3 over 2. You remember sometimes you may have to use the quadratic formula, which is given in the formula booklet. So we have 2 eigenvalues. Now, to find the eigenvectors, we want to solve a minus lambda I times some vector x gives us the 0 vector. So for lambda 1, if you put lambda 1 is equal to -3, then a minus lambda I is this matrix here. A minus lambda I, so that means we just subtract -3 on the diagonal, which means we add 3. So that's why we get 7 over 2, 1, 7 over 2, and then 1. Now, these 2 rows are the same, so the vector in this case is very simple. We just take a 1 and a minus 7 over 2. And if you multiply these out, you see you get 7 over 2, take away 7 over 2, gives you 0. And the same with row 2, 7 over 2, take away 7 over 2 gives us 0 again. So this is the eigenvector corresponding to the eigenvalue lambda 1. Now similarly, we want to find the same thing for lambda 2. So lambda 2 is 1.5. So we subtract 1.5 on the diagonal. So we look at the matrix A minus lambda I. So here is the matrix A minus lambda I. So we have a half take away 1.5. So that gives us 1/2 take away 1.5. So that gives us minus 1, and then 7 over 2 minus 7 over 2. So in this case, you can see the eigenvector in this case is simply 1, 1. So this is the eigenvector corresponding to the eigenvalue 3 over 2. And then finally, for part D, we want to prove that this mapping is not an inner product. So again, we need to find a counterexample. So if we suppose that U is a matrix with elements 1, 1, 1, 1, then the inner product of U with itself, so A1 is 1, A2 is 1, A3 is 1, A4 is 1, and similarly B1 is 1, B2 is 1, B3 is 1, and B4 is 1. So the inner product of U with itself is going to give you 1, take away 1, take away 1, which is minus 1, which is negative. But if you look at the axioms of an inner product, phi of U with U should always be greater than or equal to 0. Phi of U with U cannot be negative. And in this case it is, so therefore axiom 3 breaks down, so phi is not an inner product. And that concludes the solutions for question number 2.